There's a star at the center of our galaxy and it completes one full orbit in less than 9 years. At its closest approach, it passes within 24 astronomical units of a black hole, 4 million times the mass of our Sun. Yes, the center of our Milky Way. At that moment, that closest point, it is moving at 25,000 kilometers per second. To give you a perspective, it is 8% the speed of light. Okay, for almost everything in the universe, Newton's gravity is good enough. It navigates spacecraft through solar system. It describes the motion of the most stars orbiting Sagittarius A, the supermassive black hole at the center of our galaxy, that's Milky Way. Newton works so well for decades, astronomical tracked dozens of these stars and saw nothing wrong. But this one star, S301, is different. Its orbit doesn't close, it drifts. It drifts by 2 degrees every single pass. And the reason? It forces us to abandon the universe Newton imagined, the static universe. This star might be the one object in our galaxy that can tell us whether general relativity is the final word on gravity, or whether it cracks open at the edge of the spinning black hole, pointing towards something deeper, a theory we don't have yet. The galactic center is the only place in the universe where we can watch individual stars trace out a shape of space-time around a black hole. Every other black hole is too far, too obscured, or too isolated. But here, right here, a few dozen stars orbit close enough that their motion encodes the structure of gravity itself. A star that built this case was S2, a 16-year orbit. At its closest approach, it skims just 1,400 Schwarzschild radii from the event horizon. That's the radius of the black hole's point of no return. And in 2018, S2 made that closest approach while we were watching. The gravity instrument, 4 telescopes at the Very Large Telescope in Chile, their light combined with a precision that effectively creates a single telescope 130 meters across, tracked S2's position night after night. And for the first time, we watched a star's light stretched as it climbed out of a black hole's gravity well. The effect was exactly what Einstein predicted, a redshift of about 200 kilometers per second. On top of the star's ordinary orbital motion, the light lost energy fighting gravity. But that wasn't just all. S2's orbit itself refused to close. After one full revolution, the ellipse had shifted about 12 arc minutes. That's roughly 1/5 of a degree. A tiny angle, but measured with precision of gravity. It was undeniable. This is Schwarzschild's precision. The simplest relativistic correction, the bending of space-time around a non-rotating mass. Mercury does the same thing around the Sun at 43 arc-second per century. So slow you would need a millennia to see it. S2 confirmed that space-time curves the way Einstein said it should, at least for non-rotating black hole. But every real black hole rotates, and rotation twists space-time in a way S2, even after decades of observation, simply cannot feel. To feel that twist, you need a star that gets much, much closer. In the spring of 2023, the gravity team conducted a routine survey of the galactic center, and in one image, then another, and then another, a faint new source appeared. It sat just 14 milli-arcsecond northwest of Sagittarius A star. That's an angle so small that if you extend it across the entire galaxy, it would resolve to roughly a width of human hair, seen from 1,000 kilometers away. 4 positions. Then team did something alarming. They projected forward. By the next observing season, that star would be outside the central field of view. If they didn't act immediately, they would lose it. So they changed it. Dictated by observation in 2024, then 2025, then a careful post-diction work backward through the archival data to 2021, then 2017. 19 positions total spread across 8 years. And when they fit an orbit to those points, the numbers came out like a punch. Period 8.7 years, the shortest known orbit of any S star. Semi-major axis 83 milliarcsecond, 33% smaller than S2's orbit, making it closest star ever tracked around a supermassive black hole. Eccentricity 0.89. That number 0.89 means that orbit is not a circle. It's not even modest ellipse. It's a stretched, flattened hairpin. At its farthest point, S301 is 32,000 Schwarzschild radii from the black hole. At its closest, 136, more than 10 times deeper than S2. And at that closest point, the velocity becomes something almost incomprehensible. 25,000 kilometers per second. Let me give you that in the terms you can feel. If Sagittarius A star were placed where our Sun is, its event horizon would sit just outside Mercury's orbit, and its closest approach, S301, would pass between Uranus and Neptune, moving at 8% the speed of light. Imagine the difference. And because of this extreme orbit, something visible that S2 can only hint at, the ellipse refuses to close. With every 8.7 years orbit, the entire ellipse rotates forward by 2 degrees. 2 degrees per orbit. Now think about it. Mercury's precision, that tiny drift that first told us Newton's gravity was incomplete, accumulates over centuries. Less than 1 arcsecond per year. You can watch for human lifetime and see almost nothing. S301 precesses 2 degrees every 8.7 years. After just 180 orbits, about 1500 years, the entire ellipse would have rotated one full circle, painting a glowing rosette around the black hole. But the precession isn't the most interesting thing about S301. The most interesting thing is what we can't see yet and what it'll tell us when we can. Physics has hierarchy of corrections. When something moves at a fraction of light speed, call that fraction beta, the relativistic effect stacks up in powers. Beta squared, then beta cubed, and then higher. Beta squared effect, that's 8% of light speed, squared, about 0.6%. These are the corrections Einstein first calculated. The bending of space, the stretching of time. Schwarzschild precision, the gravitational redshift, the transverse Doppler effect. S2 confirmed these beautifully. At beta squared level, general relativity is right. But the beta cubed effect, those come from a rotating black hole, from the twist. General relativity makes a very specific prediction about rotating black holes. Its spin doesn't just curve space, it twists it like a blender, like a spoon dragged through honey. The rotation pulls space-time around with it. A star passing through this twisted region doesn't just follow the curve of static mass. It gets dragged. Its orbit tilts. Its ellipse precesses in a second independent direction. This effect is called Lense-Thirring precession and falls off as the cube of the distance. At S2's distance, 1400 Schwarzschild radii, the Lense-Thirring effect is virtually invisible. It's buried in the noise, a signal so weak you would need centuries of data to dig it out. At S301's distance, 136 Schwarzschild radii, it should leave a measurable fingerprint on the orbit. A second precession, a tilt, a twist superimposed on the twist. And this is where it gets genuinely unsettling. General relativity is almost certainly not the final theory of gravity. It does not work with quantum mechanics. At the smallest scale, the Planck scale, space-time should dissolve into quantum form of probabilities. But general relativity is smooth, classical. It has no room for that form. Dozens of alternative theories have been proposed. Scalar tensor gravity, F of R theories. TVS, the tensor vector scalar theory designed to explain away the dark matter. Most of them agree with general relativity in every test we have able to perform so far. They only diverge in conditions so extreme, so close to spinning black hole that we have never been able to access them. But S301 changes that. S301 was probably never meant to be there. It was likely one half of a binary pair, two stars orbiting each other that wandered too close to Sagittarius A star. The black hole's gravity tore that pair apart. One star flung into interstellar space at enormous speed, a hypervelocity star never to return. The other got captured. Its orbital energy bled away into the ejected companion, and it settled onto this impossibly tight, stretched ellipse, a cosmic accident, and the best lab for gravity we have ever had. We have never directly measured the spin of a supermassive black hole. Every estimate we have from X-ray data, from accretion disk models, from jet power calculations relies on assumptions. How the gas behaves, how a magnetic field thread the disk, how X-ray scatters off hot electrons near the event horizon. All indirect, all assumption laden. S301 offers something cleaner, a star acting as a pure test particle, tracing the shape of spacetime around a spinning black hole. The orbit itself encodes the answer. So, here's the frustration and the promise bound together. We can see S301 move. The gravity instrument tracks its position with micro arc second precision, 19 points across 8 years. The orbit fit is tight, the residuals are tiny. We know exactly where this star is and exactly how it's moving, but we cannot yet measure its light in detail. The galactic center is buried behind 30 magnitude of dust extinction. In optical light, completely invisible. Even in infrared, where the dust thins out somewhat, S301 is barely noticeable. Magnitude 19.3 in the K band. It's an F-type star, roughly sun-like, but wild behind a wall of galactic dust so thick that extracting a detailed spectrum right now is simply beyond our instruments. We cannot measure its radial velocity. We cannot measure its spectral lines shift at pericenter. We cannot directly observe the gravitational redshift and the transverse Doppler effect that S2 showed us so beautifully. Not yet. The next generation of telescope is coming. The giant Magellan telescope, 7 mirrors, each 8.4 meters across, combining to create 25-meter effective aperture. First light expected within the decade. Extremely large telescope, a single 39-meter mirror, the largest optical telescope ever conceived, is being built right now in the Atacama Desert, the same desert that houses the VLT. These instruments will have the light gathering power and the spectroscopic precision to extract S301's spectrum at perimeter, to measure simultaneously the gravitational redshift, the transverse Doppler shift imprinted on this single star's motion. They will test the Kerr's metric at beta cube precision for the first time in the history. And after using all these instruments, all these fancy telescopes, we don't know what we'll find. If S301's motion matches the Kerr metric perfectly, every precession, every redshift, every twist, exactly as Einstein.